Hey, okay, so I'm going to quickly just scroll through this. Okay, so, all right. Conservation of momentum. So I have hockey puck number one and hockey puck number two. So in the beginning, I don't have any vertical velocity. It's just this puck moving sideways. So one velocity vector, and this has like zero velocity in both directions. Then at the end, these two hockey pucks are kind of shooting off in these diagonal directions. And in the problem, it says that it's deflected 25 degrees away from its initial direction, which could be like any coordinate direction, but they just kind of choose it to be X and like deflect it by 25. And then we know that this puck is at a right angle to this puck. And so that's how you get the 90 there. Okay. So what do you need to do? So it's just conservation of momentum. So just like the normal momentum equations where it's like, we have momentum is equal to mass times velocity. And you just have to break it up into component directions, right? So we have the initial momentum for A in the x direction, the initial momentum for B in the x direction, because momentum is a vector, and then the final momentum for A in the x, and then the final momentum for B in the x. So that would be ma, the initial velocity of I in the x, and then mb, initial velocity of I in the x. And then we have that it's equal to the final in the x and the final in the x. So I drew like, you can see like the two x vectors right here. So VA, right, in the x, VB in the x, the initial ones. And then for final, VA in the x. So if we break up this vector into, the y and x components. So this is the x one here, right? And then this is the x1 for B. So the x1 for A and the x1 for B. So I know there's a lot of subscripts, but basically it's like x, x initial, x final for the velocities. Okay, so then I break these up. And then also notice you can say like cosine of 65 is also equal to sine of 25 degrees. So I'll let you kind of look at the triangle and kind of think about why, right? Because this would be here. Okay. So then I find what these are using the angle that I have to break up the components. And then I'm just going to plug these things into the equation, right? VBIX, 0. VAI, I have that, right? And it's 15. VAFX, I'm just going to plug it in. VBFX, plug it in. And then I end up with like an equation here. And because I know the last piece that's really important is that the mass of the two hockey pucks is the same, so I can just like cancel out all of these masses. All right, then on the other side, I'm doing the exact same thing. Okay, what are my initial ones? So if I look at both of these, what are my initial ones? There's no y velocity to start, but there is y velocity to end, right? Like if I take just the two velocity vectors and I break up and I take the y components, take those, figure what they are, and then I just plug it in. So general equation, and it's inelastic. Plug them all in. Again, I can cancel these masses. And then I get a relationship between these two. So now I have like two equations and two unknowns. So I just take like this VA right here, and I solve like for VAF is equal to VBF sine of 65 degrees over sine of 25 degrees. And then I just plug it in to where I have VAF for this one. Plug it into VAF for this one. Oh, sorry, and I forgot the right cosine of 25. Okay, so just basically, then I only have one variable. Only have one variable left. It is this guy and this guy. And so I just can rearrange and then solve for VBF. And then once I have the VBF, I can go back and use this equation and figure out VAF. Okay, so it's just, so set up everything in the x and y direction and then plug in the initial x velocities and the final x velocities and then the initial y velocities and then the final y velocities. And just pay attention to the fact that this one's negative because it's pointing down. Okay, so then you have the equations and then the goal is just to rearrange them. Okay, and then the last piece for the second part, so for an inelastic collision where they bounce off of each other, so inelastic where they stick, the total system kinetic energy is not necessarily conserved, but for an inelastic where they bounce, so like they hit and then they go off in like two different directions, we can say that the total system kinetic energy is conserved. And so at the end, he has an expression where he sets that up. And so when we plug in the velocities here, these are going to be like the magnitudes, right? So we say like the total system. So that doesn't mean that like, so like the kinetic energy that this first puck had is not going to be the same as what this puck A has here, because like it's going to bounce and some of the velocity is going to go to B as well. So it's like this, the kinetic energy for this whole system and this whole system, if it's inelastic and they bounce off. Okay, so I will just send you the notes here, but